All right, class, welcome to the first thermodynamics lecture, which is going to be a brief discussion on the topic of spontaneity. So this is under the section regarding thermochemistry. Now, in this lecture, our goal is going to be to define and compare spontaneous and non-spontaneous processes. And after our definitions, we're going to look at some real-world examples and discuss spontaneity for both physical and chemical changes, as well as the dispersal or transfer of matter and energy. So let's go ahead and get started here. So to start off, what is a spontaneous process? Well, a spontaneous process is one that will occur naturally under a given set of conditions. Now, the last part of that statement is important because almost every process can be spontaneous if the conditions are manipulated to suit the process itself. So we will talk about different conditions in a minute with some examples of this. So what's a non-spontaneous process? Okay, a non-spontaneous process is then going to be considered one that will not naturally occur under a given set of conditions, and it will require some level of work to be done. So this could be some sort of an outside driving force or some sort of energy input that helps drive the process in the reverse fashion from its normal spontaneous flow. Now, keep in mind that we can discuss both spontaneous and non-spontaneous processes for physical changes like phase shifts, if we're talking about solids, liquids, and gases, states of matter. And it can also be applied to chemical changes, as we would often find in chemical reactions. So let's consider an example involving physical change with water. So here we have listed two conditions that we're discussing. One is where some ice is going to be left out at approximately 25 degrees Celsius, and the other is going to be where we have a container of liquid with water, and that container is going to be found at 0 degrees Celsius or below, so very cold conditions. And you can easily see or imagine how spontaneity is going to be reliant on the current state of the system. So in one case, the solid to liquid transition will occur spontaneously. That's going to be at our warmer temperature. And then in the other case, with the lower temperature, we're going to expect a spontaneous shift from a liquid to a solid. So we would go through that freezing process. Now, look at the question down at the bottom here and consider what would happen if the ice was placed into an environment where there was a 75 degrees Celsius situation. So what would the speed of the transition shift be going from solid to liquid in comparison to 25 degrees Celsius in that case? And would the spontaneity of that process be changed? Okay, so hold on to those thoughts for another moment and we will come back to them. Okay, so let's now reference this in relation to chemical change. So I think most people are familiar with the concept of rusting. This is a chemical change that's often discussed in Chem 111. And we're going to consider the chemical process of rusting in which iron and oxygen form iron oxide, and that's what we typically call rust. So most people have observed rust over a period. Sometimes it can be days if the conditions are very optimal, for weeks or up to months. Without any sort of outside intervention. So you leave something that has the potential to rust out in the environment, you come back and you can see it certainly within the scope of a couple weeks. And moisture is going to help accelerate this process along. So what do you think would happen to the same frying pan that I have imaged here if it was left out in a dry desert with very low moisture? Okay, so again, I want you, when you're thinking about this, to think about the speed of rusting and whether that's going to affect the spontaneity of the rusting process. So again, spontaneity referring to whether the process will naturally occur. All right, so hopefully you are starting to see what I'm getting at here, and that's going to bring up the next topic, which is that spontaneity is not equal to, nor is it directly related to, the speed of a process. Okay? So when we start looking at this, we can have some processes that will occur almost instantly in the blink of an eye, while others can be so slow to progress that we can't even observe them to an appreciable extent during our lifetime. All right? Now, those very slow processes, that does not mean that the reaction is not occurring. It's just not occurring to us visibly with some appreciable change that we can see, but it is still spontaneous. So in the case of ice, in that hot environment, the 75 degrees Celsius environment, the process is just as spontaneous as it would be at 25 degrees Celsius. You are going to go from solid to liquid. That's the driving force there, all right? But it will take a shorter time. So the speed and the spontaneity are different. At 25 and 75 degrees Celsius, the spontaneity is the same. It's going to proceed in that direction. However, the speed, you can call it the kinetics, at which this is taking place, right, is going to go at a much quicker pace in the hot environment for that ice example. Okay, now what about the pan that we left out in the dry desert? Again, the rusting is a spontaneous process, but it's going to be slowed down significantly due to lack of moisture in the dry environment. Okay, and so we wouldn't expect to see that pan rusting nearly to the same extent as far as the amount of time that has elapsed. Now, another example, and you can see some of the images at the top of the slide here, is that of a diamond. And the book does go over this, the OpenStax book. Okay, so there's a popular saying that diamonds are forever, but that statement is technically false. All right, now again, remember, spontaneity is very condition dependent. So under regular, everyday, atmospheric conditions, okay, carbon, which is what diamonds are composed of, prefers the lower energy state of graphite compared to that of the diamond. And so diamonds that are left in this regular atmospheric state that we walk about in everyday life are destined to eventually become graphite. So a diamond technically is not forever. Now, have you ever seen a diamond turn to graphite in your lifetime? Probably not. And that's not going to be the case because it takes billions of years for this process to occur naturally. So in your lifetime, even in multiple generations of all of your heirs and lifetimes, you're not going to see this occurring at a very ready pace. All right? So for the sake of your lifespan, the diamond would be forever. However, long term, in terms of that atmospheric environment, it would not be. All right, so speaking of which, let's take a look at this video here. So this is going to be about a 1-minute clip in which there is a sample of synthetic diamonds and they are rapidly heated in order to convert them to graphite with the assistance of a torch at around 1500 degrees Celsius. So let's take a brief look at this. Okay, so there's the torch. They're going to start heating up the synthetic diamonds, and as they continue heating, I'm going to give it a minute, you'll see as it starts to cool down that these synthetic diamonds are going to have readily turned to graphite in the course of less than 1 minute. So again, all of this is very conditional in terms of your environment and the settings under which these processes are occurring. All right, so as the thermal energy starts to fade and the heat dissipates, we can see the change from the top portion there where you can still have the diamonds to the very dark graphite at the bottom. All right, so proceeding forward. Okay, so in the book, there is also a discussion of distribution of matter and energy, and that's what we're going to wrap up with here. So when we start to look at this first example, we're going to consider matter, and these images come directly from the OpenStax book. Specifically here, we have 2 round flasks, and they have a seal between them, creating a somewhat of a closed system in these environments. And the one flask is packed with gas molecules, while the other one contains nothing but empty space. So when the barrier is removed in the middle, the matter is going to uniformly disperse between the flasks, and it will stay like that after the barrier has been removed. So to frame that in another way, that is to say that statistically speaking, once the barrier is removed, the highest probability is going to be finding the particles equally distributed between both of the flasks, right? And it will be extremely unlikely that we're going to find them all back in one flask. And you can see that in the directional arrows. Spontaneous is the dispersal, the non-spontaneous is packing them all back into one area. Okay? And keep in mind that this is going to be very important in our future discussions because we are going to start talking about something called microstates and particles that occupy these states and the statistical probability of finding a particle in a certain state. So this example, I want you to kind of hold this in your memory as we're moving on to the next subject of entropy, where that's going to apply as we start discussing microstates. All right, so finally, let's take a look at energy. So it doesn't just apply to matter. We can also observe the uniform distribution of energy. And in the example that's shown here from your textbook, we can see the thermal energy or heat transfer that is occurring. So we have two objects, and it states that object Y contains more thermal energy than, object X contains more thermal energy than object Y, based on the temperature readings that we see there. Okay, so when these two objects are placed in contact with one another, the hot object will uniformly distribute its heat to the cold object until a thermal equilibrium is going to be achieved between them. And again, this is an important concept because in a couple lectures, we're going to be discussing the laws of thermodynamics. So in Chem 111, we've already gone over the first law of thermodynamics involving energy transfer and creation or destruction of energy. And we are going to discuss the second and third laws of thermodynamics in this course here. And we're going to come back to or relate back to this concept in a little bit. All right, so that will conclude the section on spontaneity. And next we are going to move on to entropy, which many people will tend to define as disorder or randomness. And one of the favorite words is chaos of a given system. So once you feel comfortable with the material that we've discussed here, why don't you go ahead and head over to the entropy lecture, which comes directly after this. So I will see everybody over there.